Greetings, viewer. Don't forget to visit my website for links to support the production of these works if you value what I'm doing. I appreciate any help you can offer. Thank you for having a look and a listen. Yours, JohnLothe. Understanding Physics, 3 volumes in 1, by Isaac Asimov. Read by JohnLothe. Chapter 3. The Laws of Motion. Inertia. Galileo's work on falling bodies was systematized a century later by the English scientist Isaac Newton, 1642 to 1727, who was born, people are fond of pointing out, in the year of Galileo's death. Newton's systematization appeared in his book Philosophiae Naturalis Principia Mathematica, Mathematical Principles of Natural Philosophy, published in 1687. The book is usually referred to simply as the Principia. Aristotle's picture of the physical universe had been lying shattered for nearly 100 years, and it was Newton who now replaced it with a new one, more subtle and more useful. The foundations of the new picture of the universe consisted of 3 generalizations concerning motion that are usually referred to as Newton's 3 laws of motion. Footnote. The important generalizations of science are brief descriptions of the behavior of the universe that are known to cover all observed cases. It is strongly felt that they will also cover all unobserved cases, here or anywhere, now or at any time. Such generalizations are sometimes called laws of nature. This is actually a poor phrase because it seems to draw an analogy with man-made law as something that is imposed and can be repealed, that can be violated at the cost of a penalty, and so on. All such analogies are misleading. It would be better, therefore, to speak of Newton's generalizations concerning motion. However, everybody calls them the laws of motion, and if I did otherwise, I would merely seem eccentric. Nevertheless, by this footnote you are warned. His first law of motion may be given thus. A body remains at rest or, if already in motion, remains in uniform motion with constant speed in a straight line, unless it is acted on by an unbalanced external force. As you can see, this first law runs counter to the Aristotelian assumption of natural place with its corollary that the natural state of an object is to be at rest in its natural place. The Newtonian view is that there is no natural place for any object. Wherever an object happens to be at rest, footnote, without any force acting upon it, it will remain at rest. Furthermore, if it happens to be in motion without any force acting upon it, it will remain in motion forever and show no tendency at all to come to rest. I'm not defining force just yet, but you undoubtedly already have a rough idea of what it means, and a proper definition will come eventually. See page 26. This tendency for motion, or for rest, to maintain itself steadily, unless made to do otherwise by some interfering force, can be viewed as a kind of laziness, a kind of unwillingness to make a change. And indeed, the first law of motion is referred to as the principle of inertia, from a Latin word meaning idleness or laziness. The habit of attributing human motivations or emotions to inanimate objects is called personification. This is a bad habit in science, though quite a common one, and I indulged in it here only to explain the word inertia. At first glance, the principle of inertia does not seem nearly as self-evident as the Aristotelian assumption of natural place. We can see with our own eyes that moving objects do indeed tend to come to a halt even when, as nearly as we can see, there is nothing to stop them. Again, if a stone is released in mid-air, it starts moving and continues moving at a faster and faster rate, even though, as nearly as we can see, there is nothing to set it into motion. Footnote. In Aristotle's time, the earth was considered a motionless body, fixed at the center of the universe. The notion of rest, therefore, had a literal meaning. What we ordinarily consider rest nowadays is a state of being motionless with respect to the surface of the earth. But we know, and Newton did too, that the earth itself is in motion about the sun and about its own axis. A body resting on the surface of the earth is therefore not really in a state of rest at all. In fact, the whole problem of what is really meant by rest and motion forced a new view of the universe in the form of what is called the theory of relativity, advanced by Albert Einstein in 1905. In this book, however, we will run into no complications if we accept the fact that by rest and motion we really mean rest with respect to the Earth's surface and motion with respect to the Earth's surface. If the principle of inertia is to hold good, we must be willing to admit the presence of subtle forces that do not make their existence very obvious. For instance, a hockey puck given a sharp push along a level cement sidewalk will travel in a straight line, to be sure, but will do so at a quickly decreasing velocity and soon come to a halt. If the same puck is given the same sharp push along a smooth layer of ice, it will travel much farther, again in a straight line, but this time at only a slowly decreasing velocity. If we experiment sufficiently, it will quickly become clear that the rougher the surface along which the puck travels, the more quickly it will come to a halt. It would seem that the tiny unevenness of the rough surface catch at the tiny unevenness of the hockey puck and slow it up. This catching of unevenness against unevenness is called friction, from a Latin word meaning rub. And the friction acts as a force that slows the puck's motion. The less the friction, the smaller the frictional force, and the more slowly the puck's velocity is decreased. On a very smooth surface, such as that of ice, friction is so low that a puck would travel for great distances. If one could imagine a horizontal surface with no friction at all, then the hockey puck would travel in a straight line at constant velocity forever. The Newtonian principle of inertia, therefore, holds exactly only in an imaginary ideal world in which no interfering forces exist, no friction, no air resistance. Next, consider a rock held in mid-air. It is at rest, but the instant we let go, it begins to move. Clearly, then, there must be some force that makes it move, since the principle of inertia requires that in the absence of a force, it remain at rest. Since the motion of the rock, if merely released, is always in the direction of the earth, the force must be exerted in that direction. Since the property that makes a rock fall had long been spoken of as gravity, it was natural to call the force that brought about the motion gravitational force, or the force of gravity. It would therefore seem that the principle of inertia depends upon a circular argument. We begin by stating that a body will behave in a certain way unless a force is acting on it. Then, whenever it turns out that a body does not behave in that way, we invent a force to account for it. Such circular argumentation would be bad indeed if we set about trying to prove Newton's first law, but we do not do this. Newton's laws of motion represent assumptions, and definitions are not subject to proof. In particular, the notion of inertia is as much an assumption as Aristotle's notion of natural plays. There is this difference between them, however. The principle of inertia has proved extremely useful in the study of physics for nearly 3 centuries now, and has involved physicists in no contradictions. For this reason, and not out of any considerations of truth, physicists hold on to the laws of motion, and will continue to do so. To be sure, The new relativistic view of the universe advanced by Einstein makes it plain that in some respects Newton's laws of motion are only approximations. At very great velocities and over very great distances, the approximations depart from reality by a considerable amount. At ordinary velocities and distance, however, the approximations are extremely good. It is sometimes said that Einstein's view of the universe disproved Newton's view. This is too simple a view. Actually, Einstein's view is more useful over a wider range of circumstances. Under ordinary circumstances, however, the Einsteinian view works out to be just about identical with the Newtonian view. In this book, ordinary circumstances only will be involved, and it will not be necessary to introduce relativity. Forces and vectors. The term force comes from the Latin word for strength, and we know its common meaning when we speak of the force of circumstance, or the force of an argument, or military force. In physics, however, force is defined by Newton's laws of motion. A force is that which can impose a change of velocity on a material body. We are conscious of such forces, usually, but not always, as muscular effort. We are conscious, furthermore, that they can be exerted in definite directions. For instance, we can exert a force on an object at rest in such a way as to cause it to move away from us, or we can exert a similar force in such a way as to cause it to move toward us. The forces are clearly exerted in different directions, and in common speech we give such forces two separate names. A force directed away from ourselves is a push. One directed toward ourselves is a pull. From this reason, a force is sometimes defined as a push or a pull, but this is actually no definition at all, for it only tells us that a force is either one kind of force or another kind of force. A quantity that has both size and direction, as force does, is a vector quantity, or simply a vector. One that has size only is a scalar quantity. For instance, distance is usually treated as a scalar quantity. An automobile can be said to have traveled a distance of 15 miles, regardless of the direction in which it was traveling. On the other hand, under certain conditions, direction does make a difference when it is combined with the size of the distance. If town B is 15 miles north of town A, then it is not enough to direct a motorist to travel 15 miles to reach town B. The direction must be specified. If he travels 15 miles north, he will get there. If he travels 15 miles east, or any direction other than north, he will not. If we call a combination of size and direction of distance traveled displacement, then we can say that displacement is a vector. The importance of differentiating between vectors and scalars is that the two are manipulated differently. For instance, in adding scalars, it is sufficient to use the ordinary addition taught in grade school. If you travel 15 miles in one direction, then travel 15 miles in another direction, the total distance you traveled is 15 plus 15, or 30 miles. Whatever the directions, the total mileage is 30. If you travel 15 miles north, then another 15 miles north, the total displacement is, to be sure, 30 miles north. Suppose, however, that you travel 15 miles north, then 15 miles east. What is your total displacement? How far, in other words, are you from your starting point? The total distance traveled is still 30 miles, but your final displacement is 21.2 miles northeast. If you travel 15 miles north and then 15 miles south, you have still traveled 30 miles altogether, but your total displacement is 0 miles, for you are back at your starting point. So there is both ordinary addition involving scalars and vector addition involving vectors. In ordinary addition, 15 plus 15 is always 30. In vector addition, 15 plus 15 can be anything from 0 to 30, depending on circumstances. Since force is a vector, two forces are added together according to the principles of vector addition. If one force is applied to a body in one direction and an exactly equal force is applied in the opposite direction, the sum of the two forces is 0. In such a case, even though forces are involved, a body subjected to them does not change its velocity. If it is at rest, it remains at rest. In fact, in every case where a body is at rest in the real world, we can feel certain that this does not mean there are no forces present to set it into motion. There are always forces present, the force of gravitation, if nothing else. If there is rest or unchanging velocity, that is because there is more than one force present, and because the vector sum of all the forces involved is 0. If the vector sum of all the forces involved is not 0, then there is an unbalanced force, mentioned in my definition of Newton's first law, or a net force. Whenever I speak of a force exerted on a body, it is to be understood that I mean a net force. A particular force may have one of several effects on a moving body. The force of gravity, for instance, is directed downward toward the ground, and a falling body, moving in the direction of the gravitational pull, travels at a greater and greater velocity, undergoing an acceleration of 9.8 meters per second squared. A body propelled upward, however, is moving in a direction opposite to that of the force of gravity. Consequently, it seems to be dragged backward by the force, moving more and more slowly. It finally comes to a halt, reverses its direction, and begins to fall. Such a slowing of velocity may be called deceleration or negative acceleration. However, it would be convenient if a particular force was always considered to produce a particular acceleration. To avoid speaking of negative acceleration, we can instead speak of negative velocity. In other words, let us consider velocity to be a vector. This means that a movement of 40 meters per second downward cannot be considered the same as a movement of 40 meters per second upward. The easiest way to distinguish between opposed quantities is to consider one positive and the other negative. Therefore, let us say that the downward motion is plus 40 meters per second, and the upward one is minus 40 meters per second. Since the downward force produces a downward acceleration. Footnote. We know from experience that if we push an object away from us, it moves away from us. If it is already moving, it moves away more rapidly. In the same way, to stop a moving body, we always exert a force in the direction opposite to its motion. Experience tells us that the acceleration produced by a force is in the same direction as the force. Acceleration being a vector too, we can express the size of the acceleration due to gravity not as merely 9.8 meters per second, but as plus 9.8 meters per second. If a body is moving at plus 40 meters per second, downward in other words, the effect of acceleration is to increase the size of the figure. Adding two positive numbers by vector addition gives results similar to those of ordinary addition. Therefore, after 1 second, the body is moving plus 49.8 meters per second. After another second, plus 59.6 meters per second, and so on. If, on the other hand, a body is moving at minus 40 meters per second upward, the vector addition of a positive quantity resembles ordinary subtraction, as far as the figure itself is concerned. After 1 second, the body will be traveling minus 30.2 meters per second. After 2 seconds, minus 20.4 meters per second. And after 4 seconds, minus 0.8 meters per second. Shortly after the 4-second mark, the body will reach a velocity of 0 meters per second, and at that point it will come to a momentary halt. It will then begin to fall, and after 5 seconds its velocity will be at plus 9.0 meters per second. As can be seen, the acceleration produced by the force of gravity is the same whether the body is moving upward or downward, and yet there is something that is different in the two cases. The body covers more and more distance each second of its downward movement, but less and less distance each second of its upward movement. The amount of distance covered per unit time can be called the velocity or speed of the body. In ordinary speech, speed and velocity are synonymous, but not so in physics. Speed is a scalar quantity and does not involve direction. Any object moving 16 meters per second north is traveling at the same speed as one moving at 16 meters per second east, but the two are traveling at different velocities. In fact, it is possible under certain circumstances to arrange a force so as to cause it to make a body move in circles. The speed, in that case, might not change at all, but the velocity, which includes direction, would be constantly changing. Of the two terms, velocity is much more frequently used by physicists, for it is the broader and more convenient term. For instance, we might define a force as that which imposes a change in the speed of a body, or its direction of motion, or both. Or we might define it as that which imposes a change in the velocity of a body, a briefer but as fully meaningful a phrase. Since a change in velocity is an acceleration, we might also define a force as that which imposes an acceleration on a body, the acceleration and force being in the same direction. Mass. Newton's first law explains the concept of a force, but something is needed to allow us to measure the strength of a force. If we define a force as something that produces an acceleration, it would seem logical to measure the size of a force by the size of the acceleration it brings about. When we restrict ourselves to one particular body, say a basketball, this makes sense. If we push the basketball along the ground with a constant force, it moves more and more quickly, and after 10 seconds, it moves with a velocity, let us say, of 2 meters per second. Its acceleration is 2 meters per second divided by 10 seconds, or 0.2 meters per second squared. If you start from scratch and do not push quite as hard, at the end of 10 seconds, the basketball may be moving only 1 meter per second. It will therefore have undergone an acceleration of 0.1 meter per second squared. Since the acceleration is twice as great in the first case, it seems fair to suppose that the force was twice as great in the first case as in the second. But if you were to apply the same forces to a solid cannonball instead of a basketball, the cannonball will not undergo anything like the previously noted accelerations. It might well take every scrap of force you can exert to get the cannonball to move at all. Again, when a basketball is rolling along at 2 meters per second, you can stop it easily enough. The velocity change from 2 meters per second to 0 meters per second requires a force to bring it about, and you can feel yourself capable of exerting sufficient force to stop the basketball. Or you can kick the basketball in mid-motion and cause it to veer in direction. A cannonball moving at 2 meters per second, however, can only be stopped by great exertion, and if it is kicked in mid-motion, it will change its direction by only a tiny amount. A cannonball, in other words, behaves as though it possesses more inertia than a basketball, and therefore requires correspondingly more force for the production of a given acceleration. Newton used the word mass to indicate the quantity of inertia possessed by a body, and his second law of motion states, The acceleration produced by a particular force acting on a body is directly proportional to the magnitude of the force and inversely proportional to the mass of the body. Now, I have already explained that when x is said to be directly proportional to y, then x equals ky. See page 19. However, in saying that x is inversely proportional to another quantity, say z, we mean that as z increases, x decreases by a corresponding amount, and vice versa. Thus, if z is increased threefold, x is reduced to 1/3. If z is increased 11-fold, x is reduced to 1/11, and so on. Mathematically, this notion of an inverse proportion is most simply expressed as x is directly proportional to 1/z. For then, when z is 3, x is 1/3. When z is doubled to 6, x is halved to 1/6, and so on. We can change the proportionality to inequality by multiplying by a constant, so that if x is inversely proportional to z, x equals k/z. If x is both directly proportional to y and inversely proportional to z, then x equals ky/z. With this in mind, let us have A represent the acceleration, F the magnitude of the force, and m the mass of the body. We can then represent Newton's second law of motion as A equals kF/m, or acceleration equals proportionality constant times magnitude of the force divided by the mass of the body. Equation 3-1. Let us next consider the units in which we will measure each quantity, turning to mass first, since we have not yet taken it into account in this book. You may think that if I say a cannonball is more massive than a basketball, I mean that it is heavier. Actually, I do not. Massive is not the same as heavy, and mass is not the same as weight, as I shall explain later in the book. See page 53. Nevertheless, there is a certain similarity between the two concepts, and they are easily confused. In common experience, as bodies grow heavier, they also grow more massive, and physicists have compounded the chance of confusion by using units of mass of a sort which non-physicists usually think of as units of weight. In the metric system, two common units for mass are the gram, gm, and the kilogram, kg. A gram is a small unit of mass. A quart of milk has a mass of about 975 grams, for example. The kilogram, as you might expect from the prefix, is equal to 1,000 grams, and represents, therefore, a trifle more than the mass of a quart of milk. In common units, mass is frequently presented in terms of ounces and pounds, these units also being used for weight. In this book, however, I shall confine myself to the metric system as far as possible, and shall use common units, quarts, for example, only when they are needed for clarity. In measuring the magnitude of a force, two quantities must be considered, acceleration and mass. Using metric units, acceleration is most commonly measured as meters per second squared, or centimeters per second squared, while mass may be measured in grams or kilograms. Conventionally, whenever distance is given in meters, the mass is given in kilograms, both being comparatively large units. On the other hand, whenever distance is given in the comparatively small centimeters, mass is given in the comparatively small grams. In either case, the unit of time is the second. Consequently, the units of many physical quantities may be compounded of centimeters, grams, and seconds in various combinations, or of meters, kilograms, and seconds in various combinations. The former is referred to as the CGS system. The latter is the MKS system. A generation or so ago, the CGS system was the more frequently used of the two. But now, the MKS system has gained in popularity. In this book, I will use both systems. In the CGS system, a unit force is described as one that will produce an acceleration of 1 centimeter per second squared on a mass of 1 gram. A unit force is therefore 1 centimeter per second squared multiplied by 1 gram. In multiplying the two algebraic quantities, A and B, we can express the product simply as AB. We manipulate units as we would algebraic quantities, but to join words together directly would be confusing. So I will make use of a hyphen, which, after all, is commonly used to join words. The product of 1 centimeter per second squared and 1 gram is therefore 1 gram times centimeter per second squared. The magnitude of the unit force. The unit of force, gram times centimeter per second squared, is frequently used by physicists, but since it is an unwieldy mouthful, it is more briefly expressed as the dyne, from a Greek word for force. Now let us solve equation 3-1 for K. This works out to K equals m times A divided by F, or K equals mass times acceleration divided by force. Equation 3-2. The value of K is the same for any consistent set of values of A, M, and F. So we may as well take simple ones. Suppose we set M equal to 1 gram and A equal to 1 centimeter per second squared. The amount of force that corresponds to such a mass and acceleration is, by our definition, 1 gram times centimeter per second squared, or 1 dyne. Inserting these values into equation 3-2, we find that K equals 1 centimeter per second squared times 1 gram divided by 1 gram times centimeter per second squared equals 1 gram times centimeter per second squared divided by 1 gram times centimeter per second squared equals 1. In this case, at least, K is a pure number. Since K is equal to 1, we find that equation 3-2 can be written as m times A divided by F equals 1, and therefore F equals m times A. Equation 3-3. Provided we use the proper sets of units, that is. If we measure mass in grams, acceleration in centimeters per second squared, and force in dynes. In the MKS system of measurement, acceleration is measured in meters per second squared and mass in kilograms. The unit of force is then defined as that amount of force which will produce an acceleration of 1 meter per second when applied to 1 kilogram of mass. The unit force in this system is therefore 1 meter per second squared multiplied by 1 kilogram, or 1 kilogram times meter per second squared. This unit of force is stated more briefly as 1 Newton, in honor of Isaac Newton, of course. Equation 3-3 is still true, then, for a second combination of consistent units, where mass is measured in kilograms, acceleration in meters per second squared, and force in newtons. From the fact that a kilogram is equal to 1,000 grams, and that a meter is equal to 100 centimeters, it follows that 1 kilogram times meter per second squared is equal to 1,000 grams, 100 centimeters per second squared, or 100,000 grams times centimeters per second squared. To put it more compactly, 1 Newton equals 100,000 dynes. Before leaving the second law of motion, let's consider the case of a body subject to no net force at all. In this case, we can say that force equals 0, so that equation 3-3 becomes mass times acceleration equals 0. But any material body must have a mass greater than 0, so the only way in which mass times acceleration can equal 0 is to have acceleration itself equal 0. In other words, if no net force acts on a body, it undergoes no acceleration and must therefore either be at rest or traveling at a constant velocity. This last remark, however, is an expression of Newton's first law of motion. It follows, then, that the second law of motion includes the first law as a special case. If the second law is stated and accepted, there is no need for the first law. The value of the first law is largely psychological. The special case of force equals 0, once accepted, frees the mind of the common sense Aristotelian notion that it is the natural tendency of objects to come to rest. With the mind thus freed, the general case can then be considered. Action and reaction. A force, to exist, must be exerted by something and upon something. It is obvious that something cannot be pushed unless something else is pushing. It should also be obvious that something cannot push unless there is something else to be pushed. You cannot imagine pushing or pulling a vacuum. A force, then, connects two bodies, and the question arises as to which body is pushing and which is being pushed. When a living organism is involved, we are used to thinking of the organism as originating the force. We think of ourselves as pushing a cannonball, and of a horse as pulling a wagon, not of the cannonball as pushing us or the wagon as pulling the horse. Where two inanimate objects are concerned, we cannot be so certain. A steel ball falling upon a marble floor is going to push against the floor when it strikes and therefore exert a force upon it. On the other hand, since the steel ball bounces, the floor must have exerted a force upon the ball. Whereas the force of the ball was exerted downward onto the floor, the force of the floor was exerted upward onto the ball. In this and in many other similar cases, there would seem to be two forces, equal in magnitude and opposite in direction. Newton made the generalization that this was always and necessarily true in all cases, and expressed it in his third law of motion. This is often stated very briefly. Quote, "For every action, there is an equal and opposite reaction." Close quote. It is for that reason that the third law is sometimes referred to as the law of action and reaction. Perhaps, however, this is not the best way of putting it. By speaking of action and reaction, we are still thinking of a living object exerting a force on some inanimate object that then responds automatically. One force, the action, seems to be more important and to precede in time the other force, the reaction. But this is not so. The two forces are of exactly equal importance from the standpoint of physics and exist simultaneously. Either can be viewed as the action or the reaction. It would be better, therefore, to state the law something like this. Whenever one body exerts a force on a second body, the second body exerts a force on the first body. These forces are equal in magnitude and opposite in direction. So phrased, the law can be called the law of interaction. The third law of motion can cause confusion. People tend to ask, if every force involves an equal and opposite counterforce, why don't the two forces always cancel out by vector addition, leaving no net force at all? If that were so, then acceleration would be impossible, and the second law would be meaningless. The answer is that two equal and opposite forces cancel out by vector addition when they are exerted on the same body. If a force were exerted on a particular rock and an equal and opposite force were also exerted on that same rock, there would be no net force. The rock, if at rest, would remain at rest no matter how large each force was. The forces might be large enough to crush the rock to powder, but they wouldn't move the rock. The law of interaction, however, involves equal and opposite forces exerted on two separate bodies. Thus, if you exert a force on a rock, the equal and opposite force is exerted by the rock on you. The rock and you each receive a single unbalanced force. If you exert a force on a rock and let go of it at the same time, the rock, in response to this single force, is accelerated in the direction of that force. That is, away from you. The second force is exerted on you, and you in turn accelerate in the direction of the second force. That is, in the direction opposite to that in which the rock went flying. Ordinarily, you are standing on rough ground, and the friction between your shoes and the ground, accentuated perhaps by muscular bracing, introduces new forces that keep you from moving. Your acceleration is therefore masked, so the true effect of the law of interaction may go unnoticed. However, if you were standing on very smooth, slippery ice and hurled a heavy rock eastward, you would go sliding westward. In the same way, the gases formed by the burning fuel in a rocket engine expand and exert a force against the interior walls of the engine, while the walls of the engine exert an equal and opposite force against the gases. The gases are forced into an acceleration downward, so that the walls and the attached rocket are forced into an acceleration upward. Every rocket that rises into the air is evidence of the validity of Newton's third law of motion. In these cases, the two objects involved are physically separate, or can be physically separated. One body can accelerate in one direction, and the other in the opposite direction. But what of the case where two bodies involved are bound together? What of a horse pulling a wagon? The wagon also pulls the horse in the opposite direction, with an equal force. Yet, horse and wagon do not accelerate in opposite directions. They are hitched together and both move in the same direction. If the forces connecting wagon and horse were the only ones involved, there would indeed be no overall movement. A wagon and horse on very slippery ice would get nowhere, no matter how the horse might flounder. On ordinary ground, there are frictional effects. The horse exerts a force on the earth, and the earth exerts a counterforce on the horse and its attached wagon. Consequently, the horse moves forward, and the earth moves backward. The earth is so much more massive than the horse that its acceleration backward, remember that the acceleration produced by a force is inversely proportionate to the mass of the body being accelerated, is completely unmeasurable. We are aware only of the horse's motion, and so it seems to us that the horse is pulling the wagon. We find it hard to imagine that the wagon is also pulling at the horse. If you enjoyed this recording, you can find more and support the production of these works at my website, JohnLothe.wordpress.com. That's www.JohnLothe.wordpress.com. Thanks for having a look and a listen. Your friend, John Lothe.